So yeah, as I mentioned in Slack, I don't really have slides, all right? It's very difficult right now with like all the schedule and stuff. Um, so, but I still like the paper, and I still want to obviously talk about it, right? So today we're gonna talk about SkyPIE, a fast and accurate oracle for object placement, right? So let's kind of talk about what problem this paper is trying to solve, right? What is object placement? What kind of object placement are they talking about, right? So in the context of this paper, they think about finding a good location for some like big chunks of data, right? So big like binary objects, pictures, videos, whatnot, some blobs of data, right? So think of services like S3, right? So and when they talk about like finding the good location, what they really mean is like where in the entire cloud they need to put this data to minimize the cost and still stay within the SLOs, right? So we may have a cloud consisting of like several regions, maybe like R1, R2, R3, right? I'll put R4, I don't know, maybe R5, right? And they want to put some objects in it, right? So maybe I put some object, like the blue object in R2, right? And then, what does it mean to have this object in R2, right? So this object, this blue object, has some kind of workload associated with it, right? So it can be accessed from different regions, right? So maybe it will be accessed from R2 itself. Maybe it will be read from R2. Maybe R5 also wants to read that object. Maybe someone from R3 also wants to read this object, right? So in this case, like this blue object, it has the workload associated with that, right? So what we want to do is we want to find like the best placement of this object, and essentially the best replication of this object as well, because maybe this R3 region that needs this blue object, maybe it's going to be too expensive to have that object transferred over the network all the time, right? So maybe we want to have a copy of this object, right? So all of a sudden, all of a sudden we have we'll have a local read for this object, right? So we have these objects, we have the data. Those objects have workloads, like how much stuff, how much do you write this object, how often do you update, how often do you read, and where do you read it from, right? And we want to optimize for cost, like given the entire cloud. And what the paper says, what people traditionally do is they look at the object, they look at its workload, right? So they define the workload as some vector W, which has like all these parameters, right? So number of puts, number of gets from, let's say, region 1, and so on and so forth, right? So given this object, given its characteristics, like where do we want to put it? And the paper says that traditionally you would look at this data, right, that defines that object, the puts, the gets, like how it's being accessed, and then you go through your system, right, through your topology, and you try all these combinations, right? You want to kind of find the best combination, and you will do it for every object, right? Like whenever the new object arrives, if we have like a green object, right, with some kind of other vector, you will run through the paces and try to find, the optimal, placement for this green object given, whatever the requirements are, whatever the access requirements are for this object. And every time, for every new object, you have to redo this whole exercise, right? And, given all the constraints and options for placing the object, it's a very hard problem, right? So it's NP hard problem, and it has like a lot of parameters and a lot of constraints. So what this paper wants to do is kind of to flip the problem, right? So instead of trying to compute the optimal placement for every object, they say, well, what if we can compute an oracle, essentially like a function that we can query later, right? So you give that vector W, the workload description of the object, into this oracle, and this oracle gives you back the optimal placement that has already been somehow pre-computed, right? So instead of pre-computing it on the fly, let's have this pre-computed and queryable. And the way they kind of approach this problem is, obviously, you cannot enumerate all possible objects that you can have in your system, right? So that's kind of infinite space here, right? So, your object may be like 1 byte different, and that's already a different object. So, you kind of want to have that oracle that can answer, these questions about every single object, but you cannot enumerate the objects ahead of time. What you can enumerate are the possible placement scenarios, right? Which is still like a lot of them, right? But you can look at a particular placement, right? So maybe for this particular green object, I can look at the placement in region 4, region 5, and maybe I have reads from region 3, region 2, and self-reads, right? So this is the placement that they will look at, the actual copies in region 4, region 5, and then accesses the reads carried out from region 2, from region 3, region 1, and so on. And they define that as a placement. So the placement is like where the data is and what regions read from what other region, right? So maybe, region 1 doesn't read from anything in this particular placement because it's too far, right? So it's outside of the outside of the SLO, right? So in this particular placement, region 1 is ignored because if we use that, that's going to be outside of the other constraints like SLO. But region 2, region 1, region 3, region 2, 4, 5, and so on. So they look at the placement, and they for each placement that they look at, they compute the cost for all possible access patterns, right? And they can do this because the cost is kind of a linear combination of different things, right? So the bigger object is, the more cost there is. So like you pay per byte. The bigger object, the more data you transfer, and again, you pay for like data transfer per byte, right? So all of these cost constraints, cost parameters, they scale linearly, right? So what they end up having is, for each placement that they enumerate, they have essentially an equation, right? Like that just sums up all the parameters and their coefficients, right? To get to the cost. So it's a kind of very linear problem at this point. If you have this linear equation, you can kind of think of it as a plane, right? So the paper has this visual example where they have for particular object, they have on for this particular object, the workload is defined as having just two dimensions, right? So the number of get accesses, right? So number of gets and the size, right? So if we look at this kind of simplified space, just 2 dimensions, right? So they can compute the placements, right? So I think in this particular example, their placement is just like one region and few different configurations in that region. So you can either put it in one type of a system or another type of a system in that one region, for the simplicity of the example. But what you end up having is, for different placement configurations, you have this different, planes, right? Obviously the real configurations are not 2-dimensional, right? So, the number of dimensions is bigger because you look for number of gets at each region, number of puts, the size of an object, and a few other parameters that kind of derive from those. Like, for example, how many bytes do you need to transfer out of a particular region, given your read workload and whatnot. But the point is, if you can come up with this linear kind of representation of the cost for a particular placement strategy, for a particular object placement, then you can query that cost or query the model of all this cost, right? You enumerate them, you have all these planes just by doing something that people in like 3D graphics have been doing all the time, right? So what you end up doing here is you shoot an array from a zero cost plane up, up the cost axis, and then you see which of these n-dimensional planes you will intersect first, right? So which of these n-dimensional planes you hit first, and that will be the plane with the with the smallest cost for that particular workload, right? For that particular workload, for that object. So that's kind of the paper in a nutshell, right? So they talk a lot more about like, the specifics and how they compute these planes, right? Because this is like, this example is very short, very simple, right? It's just like one region, 3 possible like stores in that region and with 3 different costs, right? But one thing that you can kind of see even from this example, that green plane right here, the green placement strategy, it's always the most expensive, right? So in this case, it can be pruned out, right? So again, kind of what people have done, like in graphics and in games, right? You don't want to render the objects that are like behind, some wall of something, right? So the same thing here, right? You want to prune out the planes that are not going to be visible at all, right? So the paper describes, how they kind of do this, how they minimize the number of unnecessary planes so that they only keep the ones that, are relevant for, for their use case. But yeah, they argue that by doing this, they can keep the model size reasonable enough to fit within like a GPU memory, and then you can just use the GPU to query those things, right? And the reason why you want to use GPUs is because it's all like linear equations and matrices, right? So it all like you solve all of this with just some matrix multiplication. So yeah, the paper goes into like a lot more details. Quite frankly, I'm not smart enough to understand all the details. So, these are the shortcuts I took. What I want to show is a quick, gosh, it's a long paper. So yeah, query time, right? So how long does it take to query the Oracle or compute the optimal placement for a particular object with a particular workload? What's important here is they have 5 workloads. So C1 workload, I think, is kind of a regional workload. So a handful of regions on the same continent, right? Their system is green and for the CPU version, and the orange for the GPU version. It can answer the queries in like way under 1 millisecond, versus a more traditional approach that doesn't do the pre-computation, takes about, on the order of like tens of milliseconds, right? The C5 workload is the global workload. That is like all regions of AWS and Azure, I believe, combined, all the services, so 100 and something different placement. If I'm not mistaken, if I remember the number correctly. The point is, it's like the biggest, like the most global version possible, right? And their time, especially like on the GPU, I think, yeah, the blue one is the GPU, the green one is the GPU. On the GPU one, like the query time doesn't really go that much up, right? So it's just a slightly bigger model, but the GPU can just handle it no problem. On the CPU, the query time goes up, but it's still like arguably reasonable, versus the competing approaches, which are just doing the linear programming, linear optimization. They go into like tens of seconds, to compute that placement, which is, not really good if you like need it fast. So yeah, I think I will stop my short presentation at this point.